Hello friends, in previous lecture we have studied the comparison test and limit form of comparison test for absolute convergence of series. Today in this lecture we will study ratio test, root test for absolute convergence of series. Okay. The theorem, ratio test. Let summation of n be series of non-zero real numbers. n equal to 1 to infinity be series of non-zero real numbers and a is equal to lim sup of mod of m plus 1 upon n tends to infinity, small a is equal to d min of mod of m plus 1 upon n, then first a less than 1 implies summation of n converges absolutely, Second, a greater than 1 implies summation of n equal to 1 to infinity, summation of mod n diverges Third, if a equal to capital A is equal to 1, okay, or if small a less equal 1 less equal a, then test failed. Okay. Proof. First one, suppose a is equal to supremum of mod of lim sup of mod of m plus 1 upon n tends to infinity is less than 1. Choose B belongs to R such that A is less than B less than 1. Between two numbers there are infinitely many real numbers, among that we are choosing 1. Then B is equal to A plus epsilon for some epsilon greater than 0. Now we know that if capital M is lim sup of Sn, capital M is equal to lim sup of Sn, then Sn is less than m plus epsilon for all but finitely many terms. Okay, for all but finitely many terms. Okay. Now since lim sup of mod of m plus 1 upon n tends to infinity is equal to a less than a plus epsilon is equal to b. Therefore, mod of m plus 1 upon n is less than b except for finitely many terms. Implies there exists positive integer n such that mod of m plus 1 upon n is less than b for every n greater equal n. This is your a plus epsilon, right? A plus epsilon. In general, mod of n plus 1 upon mod n, mod of n plus 2 upon mod n plus 1, mod of n plus 3 upon mod of n plus 2, and so on are less than b, are less than b. Now, for any k greater than n, k greater than n, mod of n plus k upon an is equal to mod of n plus k upon n plus k minus 1 into mod of n plus k minus 1 upon n plus k minus 2, and so on. We will get lastly mod of n plus 1 upon mod n. We will get this. Intermediate terms will get cancelled. So if I take 2 here, it is just product of 2 terms. So this is product of how many terms? K terms. So this is less than b raised to k. B raised to k. Okay. For any k, for any k belongs to a natural number set. We are getting this. Okay. And therefore, mod of n plus k is less equal mod n into b raised to k into b raised to k for every k belongs to set of natural number, belong to set of natural number. And therefore, summation of an is dominated by mod n into summation of bk, k equal to say 0 to infinity, and here n equal to 1 to infinity, n equal to 1 to infinity. Is it clear? So after some terms, as this relation hold, therefore this is dominated by this one, a. Now summation of bk, b raised to k, sorry, not bk, b raised to k. Summation of b raised to k equal to 0 to infinity, is geometric series, with ratio b belongs to 0, 1, implies this summation of b raised to k equal to 0 to infinity is equal to 1 upon 1 minus b. That is, summation of b raised to k is convergent, and therefore mod an into summation of b raised to k equal to 0 to infinity is equal to summation of k equal to 0 to infinity mod an into b raised to k is convergent series, From AB and comparison test, summation of an converges absolutely. N equal to 1 to infinity converges absolutely. Every absolutely convergent series is also convergent. So if summation of n converges absolutely means summation of mod n is convergent, implies summation of n is also convergent series. Is it clear? So thus first part is proved. First part is proved. Now second, if A is equal to Riemann form, mod of m plus 1 upon n is greater than 1, is greater than 1, then choose B belongs to 1 to A, then B is equal to A minus epsilon for some epsilon greater than 0, for some epsilon greater than 0. Now we know the result that, okay, for this epsilon greater than 0, for this epsilon greater than 0, mod of m plus 1 upon n is greater than p is equal to 1 to a, and this is also greater than 1, is greater than a minus epsilon greater than 1 for all but finitely many n's, for all but finitely many n's. Implies there exists positive integer n such that mod of n plus 1 upon n is greater than 1 for every n greater or equal to n. Implies mod of n plus 1 is greater than mod n for every n, for every n greater or equal to n, greater or equal to n. So what this implies? This implies n cannot converge to, n cannot converge to 0. Implies n can't converge to 0. That is, limit of n must not be 0. And therefore, by necessary condition for convergent series, summation of n must be divergent series. Therefore, by necessary condition, for convergent series, summation of n equal to 1 to infinity is divergent series. Is divergent series. Is it clear? Case 3, if A is less equal 1 less equal A, then test fail. Then to show test fail. So for divergent series, summation of divergent series, summation of 1 upon n is equal to summation an limit n tends to infinity of mod of m plus 1 upon n is equal to limit n tends to infinity of n plus 1 upon n is equal to limit of n into 1 plus 1 by n upon n, which is 1 plus 0 is 1. While for convergent series, summation of 1 by n square is equal to summation n. Why it is convergent? We have not proved till summation of 1 by n square is convergent. Okay. So for convergent series, this limit n tends to infinity of mod of n plus 1 upon n is limit of. If limit of given sequence exists, then its lim sup and lim inf are same and they are equal to limit of that sequence. So limit of n plus 1 upon n is nothing but n plus 1 bracket square upon n square, which is limit of n square in bracket 1 plus 1 by n bracket square upon n square. This n square gets cancelled and it will again become 1 plus 0 is equal to 1. Okay. So thus test fail for a equal to a less equal 1 less equal capital A. Thus ratio test is not applicable if a less equal 1 less equal a. Okay. Now discuss the convergence of series by ratio test for summation of n factorial upon n raised to n. Example, discuss convergence of series A summation of n factorial upon n raised to n equal to 1 to infinity, and B summation of n raised to n upon n factorial n equal to 1 to infinity. Solution for series A, for series summation of n factorial upon n raised to n equal to 1 to infinity equal to summation n limit n plus 1 upon n. If I take mod of this, it is n plus 1 upon n because that terms are positive. So we will get n plus 1 factorial upon n plus 1 raised to n plus 1 into reciprocal of n raised to n upon n factorial, which is equal to n plus 1 into n factorial into n raised to n upon here n plus 1 into n raised to n plus 1 raised to n into n factorial. This n factorial will get cancelled, n plus 1 will get cancelled by taking n raised to n outside. 1 plus 1 upon n raised to n, this get cancelled. Okay. Therefore, limit n tends to infinity of limit n tends to infinity of mod of n plus 1 upon n, which is equal to limit of 1 upon 1 plus 1 upon n raised to n, which is equal to 1 upon e less than 1. Is it right? And which is also lim sup. Therefore, by ratio test, summation of n factorial upon n raised to n equal to 1 to infinity is convergent. B Okay. By calculation in A, limit n tends to infinity of, for series, summation of n raised to n upon n factorial is equal to summation an limit n tends to infinity of mod n plus 1 upon an will become e greater than 1, and therefore this is your limit also. Is greater than 1, therefore by ratio test summation of n raised to n upon n factorial is divergent. Is divergent series. Okay. So that summation of n equal to 0 to infinity x raised to n upon n factorial is convergent for any x belongs to R. X belongs to R. Solution. For x equal to 0, summation of x raised to n upon n factorial n equal to 0 to infinity is 0. If x is 0, we will get this. So, if x is not equal to 0, then for series summation of x raised to n upon n factorial n equal to 0 to infinity limit, or if I denote this by summation an limit n tends to infinity of mod of n plus 1 upon an equal to, or if I take firstly this, okay, mod of x raised to n plus 1 upon n plus 1 factorial into n factorial upon x raised to n, which is equal to mod of x raised to n into x into n factorial upon n plus 1 into n factorial into x raised to n get cancelled, n factorial get cancelled, and which is nothing but 0 less than 1. Therefore, by ratio test, summation of 0. So this is the mod of x upon n plus 1 tends to 0 as n tends to infinity. Ratio test, summation of x raised to n upon n factorial n equal to 0 to infinity is convergent for any x belongs to R. 0 less than 1. 0 less than 1. So its limit is less than 1. So if limit exists, then lim sup of mod n plus 1 upon n is also 1. Is it clear? So with this discussion, we will stop our lecture on ratio test here. Thanks for listening lecture carefully. Bye bye.